So, questions from the homework? Yep.
Can you do number 5 quick?
Love to. Okay. Number 5, which bulb is brightest? Really what we're saying then is which bulb has the biggest, the most power? Are they identical?
Yeah.
Then you know what? I'm going to give them each a resistance. I'm going to say, hey, that's 2 ohms, that's 2 ohms, and that's 2 ohms. Just because. Okay? Now, power equals VI. That's true, but I don't know the voltage drop in any of these. I don't know how it splits up. So what I'm going to say is power equals I squared R. That was another version of power. Each of them has the same resistance. So this isn't going to affect my answer at all, isn't going to affect the brightness at all. What will affect the brightness? Which of those bulbs, A, B, or C, has the most current flowing through it?
A.
Why? This has I total, and then this, in fact, I can even tell you, because the resistors are identical, it's going to be split up 50-50. Got to be A. Got to be A. Has to be. If I had more numbers, I could actually even probably crunch some numbers. In fact, after today, you would be able to actually go further than this and tell me what the current breakup, all sorts of things, but
Okay.
after today's lesson.
Because what I did was from the P equals VI, and I just like made up a number from I and then just.
Okay, that also works. The problem is I don't know how the voltage break goes. 10 volts, I don't know if this loses 6 volts and then each of these does 4 volts. I don't know. I need more information before I can get that far. I'd have to do some number crunching. I certainly can't say 10 volts, 10 volts, 10 volts. That's an illegal ski hill,
Okay.
right? If I ski this path, I have to lose 10 volts total. If I ski this path, I have to lose 10 volts total. And I also know those two will be the same height, but not the first one. Might be, but probably not. Is that okay?
Yeah.
Any others? Yep. Yep. Any others? 12? Love to. Okay. First thing I always look for is total current. Do I see it anywhere blatantly? What I mean by that, Kayvon, is I'm looking kind of in this section and in this section where there's no junctions. I don't know. Next, I'm going to see, can I figure out total current? Well, I know down this hill how many amps. I know down this hill how many amps. So using Kirchhoff's law, can you tell me how many amps right here? Total current. Got it. This question's going to fall apart, I'm confident. Now I'm going to start to slowly ski and walk my way through. Probably the next thing that I would look for is anywhere that I have 2 pieces of information. I notice I have 2 pieces of information on this resistor here. If I know 2, I know 4. Although since they're not asking for power, I'll say if I know 2, I know 3. If I know any of I and R and V, I know the third one. So I know I know R. What's the voltage that we lose here? You're right, say it loudly. Okay, Vaughn, you like to ski? Let's go skiing. Ready? Start at the end of the chairlift. How high have we left the chairlift at? Always going downhill. What did I lose going through this hill? I don't know how high that hill is, but was I able to get to the bottom? What must I lose in that hill? Has to be. Has to be. Ooh, not only that, I know the current in that hill. Gotta be. Do I know 2? I know 3. R equals V over I. You know what? That's going to be a 20 ohm resistor, right? R equals V over I. Okay, I've analyzed that path. Let's go skiing. Let's ski down this hill. How high is the chairlift? We only went down one hill and got back down to the ground. How high must that one hill be? Gotta be. Do you know now 2? Do you now know 2? Then you know 3. That's going to be a 60 ohm. See what I mean? Once you have the total current, then it's just look for ski hill, continuous paths, and it usually falls apart. By the way, the other thing I could have said is instead of skiing this whole thing to find that final resistor voltage, I could have said, you know what? If we were able to shake hands here and meet up here, then this hill and this hill better be the same voltage. 120 down the middle two hills, the one big hill must be 120 as well. Right? Any others? Nope. Is that okay? Yeah, yeah? This is the one class where everybody has moved forward, and my other ones I got empty in the front. Sorry. You could always sit further forward during the lesson if you wanted to. Anyways, can you hand in lesson 3 if it's done? Folks, if you have not finished lesson 3, your job this weekend is to get lesson 3 and today's lesson 4 caught up. You do that and you understand it, you're in great shape to get at least a B on this test, probably an A. Probably an A. Speaking of, once you've handed in lesson 3, lesson 4. If lesson 3 was the meat and potatoes of this unit, the fundamental portion of this unit, lesson 4 is the gravy. And you're going to need your calculator out. So get it out, please. You're going to need your calculator out. What we want to talk about are the two main types of circuits, series and parallel. Yep. Series and parallel. So a series circuit is a circuit where the resistors are connected in a row with no junctions between them. In my ski hill analogy, a series circuit is a circuit where the skiers all ski the same path. Which circuit has resistors in simple series, the top one or the bottom one? Because all the same skiers go through here and here. Here, there's a junction. Does anybody know what we call that type of a circuit? That type of, that's going to be a parallel section. We'll come back to that, okay? So, not series. That first one is series. Who remembers what I said? If we're analyzing a circuit, if we're solving a circuit, what do we try and find first? What did I say? What do we look for first? Total current. What if they don't give it to us? I said, go look and see if there's a resistor, if there's, where they gave me two things. What if that doesn't occur? Our strategy now is going to be, can we mathematically rewrite a yucky circuit into the simplest possible circuit? And the simplest possible circuit, don't write this down, has one voltage source and one resistor. One chairlift, one ski hill. That's going to be what I'm going to teach you how to do today. That's going to be our strategy. So example 2 says, find an expression for the total resistance of a series circuit. I was going to do a lovely algebraic proof, but I'm just going to actually give you the answer. If this is, write this down, 3 ohms, and if R2 is 4 ohms, and if R3 is 7 ohms, and they are all in series, so 3, 4, 7, our total is 3 plus 4 plus 7. That you can do in your head. Ohms. In other words, Enzo, these two circuits are mathematically equivalent. The real circuit and this virtual circuit that has a voltage and a single 14 ohm resistor, those are mathematically the same. What that means is, supposing I told you that the voltage was 42 volts. In that big circuit, in the original, you would say, oh, I'll look for total current. Have they told me total current anywhere? No. Then you would say, oh, I'll look for a resistor where they've told me two things. Have they given me a resistor with two things anywhere? No. Then you would say, my strategy is going to be rewrite this as the mathematical equivalent. So my mathematical equivalent has a chairlift of 42 volts and one resistor of 14 ohms. Why does that help? What can I find now? Well, let's see. Let's go skiing. How high is the chairlift? What must I lose if there's only one hill? And now what I've done is not ohms, Mr. Dueck. I now have a mathematical resistor that does have two pieces of information. What else can I find in that resistor? What's the current flowing through that resistor? I equals V over R. What's the current flowing through that resistor?
3 amps.
Why is that so nice? Isn't that the current flowing, right there? And that is not virtual. That's total current. Now let's go back to our original circuit. 3 amps is leaving the chairlift. How many amps going through R1? 3 amps. How many volts do we lose going through R1? Do the math. V equals I times R. If I know 2, I know 3. I know the current, I know the resistance. How many volts do I lose going through R1? Or is that a German saying no, Till? Yeah, 9. 9? No? Yeah, okay. Hey, how many amps going through R2? 3 amps. How many volts do I lose in R2? 12. How many amps going through, what's the current? How many amps going through R3? Still 3. How many volts must I lose? 21. And there, I've just solved the circuit. So our strategy is going to be look for total current first, look for a pair next. If that doesn't work, find the mathematical equivalent, and that'll let you find total current. Sand, you with me, or have I lost you?
No.
Here's what I heard. No.
Well, I was just curious of like how did the volts split up?
Okay, try it again. Ask me leave your pen alone. Ask me the question.
The volt.
So are you okay with my mathematical equivalent down here?
Yeah.
So because it's 42 volts high and mathematically I only have one hill, I must lose 42 volts, right? And so then I went V divided by R. Total current is 3. You okay with that?
Yeah.
So how many amps right there? How many amps right there? How many amps right there? How many amps in this resistor? 3. How many ohms? I times R. Got to be 9 volts, right? How many amps going through this resistor? Still, because the skiers don't vanish. How many ohms for what voltage? Got to be 12? Got to be 21. I just made that up. Okay, I just said suppose that was a 42 volt battery. Generally, I'm going to give you the chairlift, or if not, you'll be able to figure it out. We'll do one like that too. So, in the box on the next page, if you're in, and again, this is key, series, you want to find total resistance? Add them up. Add them up. R1 plus R2 plus R3 plus R dot, 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 dot. Example 3 says, select the best answer for the voltage drop across the 20 ohm resistor. Is that 20 ohm resistor going to be 100 volts, more than 50, less than 50? We're going to be more specific. We're going to find the exact voltage drop. Step 1, look for total current. Did they give me total current? No. Step 2, look for a resistor. Really, you're dropping stuff like crazy here, but that's okay. That's okay. I'm just glad you're here. Look for a resistor with 2 pieces of information. Is there a resistor with 2 pieces of information anywhere? No. Step 3, write the mathematical equivalent. Those 2 resistors, the 5 and the 20, are they in series? That's the same as, and now, Tanisha, you can see they gave me the 100 volts. And one resistor of why does that help? Because now I total is always going to be voltage total divided by resistance total. What's the total voltage? It's probably going to be the chairlift, because that's how high your mountain is. What's the total voltage in this question? What's the mathematically equivalent total resistance in this question? How many amps are totally in this circuit? In other words, how many skiers are leaving the chairlift? And now this question is going to fall apart. Let's go skiing. So right here, I know is 4 amps. Right here, I know is 4 amps. Aha! In this first resistor, how many amps? Really? Right here, I know is 4 amps. Right here, I know is 4 amps. So in this first resistor, how many amps? 4. No delay this time. I now know 2. That means I know 3. What's the voltage drop in that first resistor? Ning. 20. Keep going. How many amps in this second resistor? Still. How many amps in the second resistor? Still. So how many volts do we lose? So the answer is more than 50, and I'm going to say exactly 80 volts. Where's my proof? Right there. Our strategy is going to be, okay, find I total first if you can. If not, find a pair. If not, rewrite the circuit mathematically. Find I total, and I total is always going to be V total divided by R total, and V total is almost always going to be the chairlift, the battery, the height of the mountain. Example 4 says, find total resistance and current, and then find the current and voltage drop through each resistor. You know what? Solve this circuit. What that means is find 3 things on every resistor, or if they ask you, actually, to be honest, we could find 4. We could find power as well, because it's V times I. I'm not going to do power today because it just clutters up the diagrams, but understand if you know 2, you know 4. I flogged that to death last lesson. All right. Did they tell me total current? Did they give me a pair? Do I have a resistor with a pair of things anywhere? So I'm going to rewrite this as the mathematical equivalence. Okay? What's R total? Are these in series?
Yeah.
It's going to be 15 plus 5 plus 5. I think I can do that in my head. You know what? This is the same as one 25 ohm resistor. Until you get good, it's worth sketching the virtual equivalent. I always just go boom, boom. And if you really want to be lazy, you can just go 25 ohms, or you can do the resistor symbol. I don't care. This is just a sketch. 100 volts is what the diagram said. So, key to doing this question. It did say find total resistance. I did. I'll put a box around that because that's one thing they wanted me to find. And in terms of if I gave you a question like this, this is the amount of work I would like to see. I would like to see some work somewhere. So I'd like to see how you calculated total resistance. I total is going to be V total over R total. What's the total voltage? 100? Total resistance? 4.0 amps. That's what else they all wanted me to find. Who's up for some skiing? Let's leave the chairlift. How many amps are leaving the chairlift? 4 amps. Let's keep going. Let's keep going. Let's keep going. How many amps go down this first hill? How many volts is this first hill? How high is this first hill? How many volts do we lose going through this first resistor? Let's keep going. Let's keep going. How many skiers, how many amps go down this second hill?
4 amps.
Still 4 amps. How many volts do we lose going through this second hill? 20 volts. Let's keep going. Let's keep going. Let's keep. How many amps go through this third hill? How many volts? Have I solved this? It said find the total resistance, check. Total current, check. And then find the current through and the voltage drop across each resistor, check, 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 check. Parallel These ones, a little tougher. This is where you're going to need a calculator. So this is where you don't want your calculator out. This is where you're going to want your calculator out. This is where you're going to want to have a calculator out. This is where you're going to need a calculator. Do we have a calculator here today? A parallel circuit is a circuit where the resistors start and end at the same voltage, the same height, but they go in different pathways, different hills. Which circuit shows resistors in simple parallel? Top one or bottom one? Top one. What we're saying is the skiers can shake hands. Some can go this way, some can go this way, some can go this way, but they all meet up again. That's a parallel circuit. This one has those two in series. And then there's kind of a complicated parallel thing here because you can shake hands and meet up. But simple parallel, more complicated. We'll get to that one. Example 6 says, find an expression for the total resistance. And I was going to cave on, do a lovely little proof. I'm not. By the way, this is much tougher than the previous. This is where you want to focus. You know what? You cannot find total resistance of a parallel circuit. All you can find is its reciprocal. That's why it doesn't say total resistance. It says total resistance 1 over R total. And to find 1 over R total, it turns out it's 1 over R1 plus 1 over R2 plus 1 over R3. In other words, looking at this circuit up here, let's make the left-hand resistor 4 ohms. The middle resistor 4 ohms. And the right-hand resistor 8 ohms. And just for fun, let's make this battery 48 volts. What if I said find total current? Or what if I said find the current in each resistor? Problem. Do I know total current? No. Do I have a pair anywhere? No. Okay. Then what I would do is I would find total resistance. What I want to do is I want to write this as its mathematical equivalent of 48 volts and 1 resistor. How do I find R total? I can't. What I can find is 1 over R total, which is going to be 1 over 4 plus 1 over 4 plus 1 over 8. On your calculator, go 1 over divided by 4 plus 1 divided by 4 plus 1 divided by 8 and hit equals. That is not our total, but you should try it, please, 0.625, yes? That's not the total resistance, that's its reciprocal. I want the reciprocal, I want 1 over this, and conveniently, Enzo, you all have a 1 over button on your calculator. It looks like one of two things. Look up, look up, look up, look up. Either it's a little x to the -1 button, or it's a 1 over x button. That will take the reciprocal of that answer when you press equals. So your job right now on your calculator is to find that button and see if you get an equivalent resistance of 1.6 ohms. If you can't find it, I'm going to come help you. So here's what that says. I can replace those 3 parallel resistors with 1 resistor. How big? Psst. I can replace those 3 parallel resistors with 1 resistor. How big? In other words, on my sketch, why is that so handy? Because I total equals V total over R total. Total voltage, what did I say it was, 48? Total resistance, 1.6. What's the current leaving the chairlift? 30 amps. Right here, 30 amps. Not only that, Enzo, you want to go skiing? Let's go skiing. Enzo, my friend, can I ski like that and get to the bottom? Yes. You sound so uncertain. Yes. Ready, Enzo? Yes. Downhill, downhill, downhill. I'm going to go down this one. Can I get to the bottom of the chairlift, always going downhill that way? Say yes. Yes. How high is the chairlift?
40.
Enzo, how high is the chairlift? 48 volts. How high must this hill be if I was able to get to the bottom? I must lose 48 volts in that hill. Do I know 2? I know 3. What's the current in that particular resistor? Please do this, folks. I see a bunch of you just sitting there. I'm not doing these. What's the current in that resistor? It must be 12 amps. Hey, Doug, let's go skiing on this hill. How high must this hill be? Turns out it's also 48 volts. What's the current flowing through this resistor? Also 12 amps. Jordan, let's go skiing. How high is this hill over here? That's the resistor. How high, how many volts must I lose going through that hill? Jordan, how high is the chairlift?
48 volts.
And if this is the only hill I go down, how much must I lose going through there? How high is the chairlift?
48.
How much must I lose going through this hill if I get to the bottom? No calculator.
48.
I have to lose 48 volts. You better do the homework. I must, if I gain 48, I must be losing 48. This is Kirchhoff's law. Okay? By the way, folks, if you guys haven't done lesson 3, you have to do it this weekend. Otherwise, you're setting yourself up for ugliness. You hear me? You better get the homework done this weekend, okay? You gain, look up. You gain 48. I can go through here and get back to the bottom. I have to lose how many amps? Now do the math. What's your question, Jordan? This is a good question. Ask. This is fundamental. Ask.
Well, I don't even know what question you're asking.
What?
Did you enter?
Anyways, how many amps? 6? How many amps grand total? Does that double check with what we got down here? We've just proved the parallel rule, right? 12 plus 12 plus 6 is 30. We were able to find it using Kirchhoff's laws. We were also able to find it using the parallel law. We've just proved it. So, in the box on the next page, to find parallel, 1 over R total equals 1 over R1 plus 1 over R2 plus 1 over R3 plus. And then take the reciprocal. Okay? And then take the reciprocal. Example 7 says find R total and I total and then V and I for all resistors. Okay. So what I'm going to do is I'm going to find the mathematically equivalent circuit. This one, with a voltage of 60 and a mystery single resistor. Did they give me total current? Go look. Anywhere? No. Did they give me a resistor with 2 pieces of information? No. So the first thing I'm going to do is I'm going to say these 3 resistors are in parallel with each other because we split up here and rejoin here. So 1 over, my symbol for R parallel is often R parallel, but since it's total, I'll go 1 over R total. 1 over 10, 1 over 15, 1 over 20. What is the total resistance of this circuit? I get that. They're not always going to work out evenly. I'm going to carry this to a few extra sig figs. I'm going to write down 4.6154, but I'll store this answer on my calculator. Units, what do we measure resistance in? Ohm. So this is 4.6154 ohm. Question? And don't use your fraction. 1 divided by 10 plus 1 divided by 15 plus 1 divided by 20 equals reciprocal equals. Okay? No, exactly like that. Not, but type it that way. 1 divided by 10 plus 1 divided by 15 plus 1 divided by 20 equals reciprocal button equals, and you'll be there. Hey, what's I total? Well, that's going to be V total divided by R total. What's the total voltage in this circuit? Total resistance, 4.6154. You know what? I'm going to go 60 divided by, I'm going to use my answer button. What's the total current in this circuit? Oh, 13 even? Nice. So going back to my original circuit then, what that means is I have 13 amps going off that way. Not only that, so Jordan, I was raising my voice earlier. Let me go a bit slower. Here's what we're saying. Whatever voltage you gain, if you are from the battery, if you are able to arrive back here, you must lose that voltage. So you ready, Jordan? We're going to go skiing again. Follow me. How high are we when we leave the chairlift? 60 volts. If I go down this hill, can I get to the bottom? So how many volts must I lose in that middle hill? Have to. So all of us, let's label this with 60 volts. But also, Jordan, I could have gone that way. How high must this hill, this resistor, how many volts must I lose going through that resistor? Yes. Stop that, Doug. How many volts must I lose going through the right-hand resistor? Now, in each of these, do I now know 2 things? Then I know 3 things. What's the current going through here? Current is V over R, 60 divided by 10. That's 6 amps. What about here? What's the current going through the middle resistor? 60 divided by 15, 4 amps. And what's the current going through here? 60 divided by 20. Double check, does that add to 13 amps? Do we have 13 amps of skiers?
Yeah.
We've just proved that the parallel law works. Okay. Ryan, I could actually have solved this without doing this step, but what I'm saying, because I could have found, I did the voltages and the currents without actually using the 1 over R2 and reciprocal. But the fact that I was able to get that total using that, I've just convinced myself that that reciprocal rule works. Okay? Example 8. What can be said about the voltage drops across the resistors in the circuit below? What do you notice they didn't give you in example 8? Okay, I don't know total voltage. But you know what? If I can add up the hills, as long as I'm always going downhill, don't go back uphill. That's another way to find out how. I can find out how high the mountain is either by measuring the height of the chairlift or by keeping track of how far down I have to go to get to the bottom. Either way, I'll get the total voltage. Did they tell me total current?
Yeah.
Oh, cool. That's going to help. Did they give me a pair anywhere? Nope. Okay. There is one set of resistors that interests me. This one, don't circle it. What do I like about those 2 resistors? They are So what can you tell me about how the current splits up in those guys? You know what? That's going to give me a good starting point. I can, I think, assume 2.5 amps, 2.5 amps. Splits up. We did say if the resistors are identical, it'll split up 50-50. Do I know two? Yes. What's the voltage in that top one? Heck, what's the voltage in the bottom one? You lose 30 volts. In fact, Kayvon, I really didn't need to do both of them. Can I shake hands here, because this is downhill, and meet up here? Then you know what? Each of those resistors must be the same height, same voltage drop. Can I shake hands here and meet up here?
Yeah.
Then what can you tell me about the voltage here and the voltage here? They're the same. If I find one, I'll know the other. Can I shake hands here, meet up here? The voltage in each of those is going to be the same. Not the current, because the resistors are different, but the voltage will be. Let's keep that in mind. Okay. Let's look at this guy. I do notice 20 and 5 is a 4-to-1 ratio. With 5 amps, I think it's going to break up in a 4-to-1 ratio. I think one of them is going to be 4 amps, one's going to be 1 amp. This is that shortcut that I said I hardly ever use, but I am mentioning it. And the smaller resistor has the bigger current. I'm pretty sure it's going to be 4 amps, 1 amp. But if you didn't spot that, no problem. Don't need to worry about that. So if I lost you, don't freak out. Here's what I noticed. Sanj, these two resistors are in parallel. So mathematically, I'm going to write the equivalent 1 resistor. 1 over R parallel equals 1 over 20 plus 1 over 5. If I replace that 20 and that 5 with 1 resistor, go, what would I replace it with? Please do this on your calculator. Jordan, please do this on your guys, you got to be with me here. I feel like I'm treading water in tar and jello or something. I'm just resisting. You guys got to be active here. Doug, what'd you get?
4.
This is the same as a... Now, why is that so handy? Look up, look up, look up, look up, look up. How many amps are flowing in right there? So, how many amps must be going through this mathematical equivalent resistor? Doug? Let's write that down. How many volts must we lose through this mathematical equivalent resistor then? Each of these has to be a 20-volt high hill. Has to be. Because I said mathematically we must lose 20 volts going through there. I replaced those two with the mathematical equivalent Kayvon. I knew the current going through them. Oh, now, do I know 2 things? I know 3 things. What's the current going through the left-hand resistor? 1 amp, right? V over R. What's the current going through the right-hand resistor? 4 amps. Let's do the same thing over here in the top left corner. I'm going to replace this with 1 equivalent resistor. I have a 10, I have a 15, so that's going to be 1 over R parallel equals 1 over 10 plus 1 over 15. Mathematically, those two in parallel are the same as what? Go to your calculator.
6 watts.
Sanj, question? So what's the equivalent resistor? Sorry? 6? You guys are doing this, yes? Yeah, okay. So 6 ohms? Ooh, how many amps are going through this section? 5 amps. How many volts must I lose going through this section? Must lose 30 volts. Oh, so that hill is 30 volts high, and that hill is 30 volts high. What's the current flowing through the very tippy top resistor? Got to be 3 amps What's the current flowing through the bottom resistor of that group? Got to be 2 amps. And again, Kayvon, you'll notice I can get that too by going 30 divided by 15, or I can say, well, I got 5 amps, 3 went that way, 2 went that way. What we're also doing is we're confirming we got multiple methods to get the same answer. We're confirming that Kirchhoff's laws and the circuit rules work, all based on Ohm's law.
Where did you get the 6 ohms from?
I don't know. Somebody went 1 divided by 10 plus 1 divided by 15 reciprocal? Yeah. Right there, right? 10 ohms, 15 ohms, 1 over 10, 1. Yeah? I didn't do it. I'm assuming other people did. They called it out. Is that okay? Last thing. How high is the battery? What's the voltage of the battery? Let's go skiing. Doug says 80. Let's see. How high is this pair of hills? 30. Doesn't matter which way you go, but 30. Then you can go that way or that way, but no matter what, you'll lose. That's 50. And then you can go that way or that way, no matter what, you'll lose. How high must this hill be? Battery's got to be an 80-volt battery. Has to be. 80-volt voltage source. Okay. Couple of handy little tricks. So it says, example 8 illustrates an important point. Guys? Example 8 illustrates an important point. It says that if you happen to notice that 2 resistors are in parallel, like these two, if you know the voltage in one, you know the voltage in the other. Drop. If you know the voltage drop in one, you know the voltage drop in it has to be, because if the skiers can shake hands and then meet up, they must go through the same height. Or they're having to ski uphill. Nope. That's illegal. Another thing I want you to notice. What was this resistance right here? Just read it to me. What about this one? What was the total? 6, smaller than the 10 and the 15. What was the resistance here? What was the resistance here? What was the equivalent? 4, smaller than the smallest resistor in my parallel. Just as a built-in error check, Ryan, if you are finding an equivalent parallel resistance, I can tell you ahead of time, the new parallel resistance will be smaller than the smallest resistor that was in your parallel set. So for example, if you were doing 1 over R parallel, 1 over R, 1 over, and one of the resistors was 2 ohms, I can tell you the answer is going to be less than 2 ohms. I don't know what, but I can tell you it's going to be less than 2. Okay? If you get something different, you probably forgot to take the reciprocal or something like that. Let's talk about how you blow a breaker. In a household circuit, plugs and lights are wired in parallel to 120 volts AC. Each circuit has a circuit breaker in the circuit. The circuit breaker is an automatic switch that opens when the circuit exceeds a set value. For almost all of your plugs, it's 15 amps. You have a few plugs that are 30 amps. The stove plug, the dryer plug, and you might have a couple more. But the vast majority of them, you try and get more than 15 amps, you're going to blow the breaker. So, example 9. If we connect a 1500 watt hair dryer and a 500 watt TV to the same circuit, will we blow the breaker? Here's our circuit. Let's redraw it as a schematic. Now, we are using an AC voltage source, but the physics still works. The symbol for an AC voltage source, don't write this down, is not that. That's for direct voltage for a battery. The symbol for an AC voltage source is a circle with a little wavy line to show voltage goes up, voltage goes down, like a little sine wave. So draw that and then put a little 120 volts next to it. Draw that and then put a little 120 volts next to it. Then it looks like our circuit goes, we have one resistor here, there's the blow dryer. And it has, and one resistor here, there's the TV. There's our equivalent schematic, our circuit drawing. What did they tell me about the hairdryer? 120 what? Or sorry, 1200 watts? And what was the TV? Sorry? 500 watts. Okay, so here's the information that they gave me. Did they tell me total current anywhere? Nope. Did they tell me anything with two things on it? No? Let's go skiing. Let's go skiing. Whose phone was that? Kayvon, that wasn't your phone again, was it? So the Timbits that you owe us already that you didn't get today that you said you'd put on your phone for today. So now it's 2. Can you put your phone on vibrate, please? Okay. Kayvon, let's go skiing. Ready? Ready? Ready, ready, ready? Watch. How high? Can I get back to the bottom like that? How high must the 1200 watt, how many volts must I lose in that 1200 watt hairdryer? Nope, I didn't want to do that. Didn't want to do that. Well, okay. Kayvon, let's go skiing. Gotta be, right? Now, this is alternating current, which means you can ski in either direction. I'm not going to get into that part. But for what it's worth, the physics says I better lose 120 volts through each of those resistors. Do I know 2 things now? Then I know 4 things. This time they gave us power, so I'm going to have to use power equals VI. That was Joule's law from last day, or from 2 days ago. So can you get the I, because they're asking about current. Can you get the I by itself? How? More specific, I equals what? Okay. So how many amps going through that portion of the circuit? $10 amps. How many amps going through this portion of the circuit? Don't think it works out evenly. Okay, so I'm going to go 4.17. What's the total current in this circuit? Are we going to blow the breaker? Are we close? In fact, I'll tell you what might happen, and I got to go real life now. You see, in our magic physics world, I've been pretending that these wires have no resistance. In real life, because you're so close to tripping the breaker, you might find after 2 or 3 minutes the breaker breaks. And what's happened is the wires have been slowly heating up a little bit at a time, and as they heat up, their resistance increases because inside the wires now the molecules are moving faster and it's harder for the electrons to go through, which means they heat up the wires a bit more, which means the wires resistance increases even more, and that might put you over the top. That's why sometimes when you plug something in, the breaker doesn't blow right away. It takes a couple of minutes, and then the breaker blows. You're probably right at like 14.8 amps or 14.9 amps, and it was that little bit of wire heating up, increasing the overall total resistance, which we're ignoring, that put you over the top. Certainly, you could not plug anything else in. This is how you blow a breaker. Okay? So, will you blow the breaker? You will almost. Not quite. 14.2 amps. You're flirting with it. In fact, you may even find if instead of a blow dryer, well, okay, if this was your blow dryer and this is what it was drawing on low, you may find flipping it to high, that might trip the breaker. Okay? What's your homework? Here's what I assigned my block F's. I'm giving you lots. 1, 2, 3. Okay, let me write that down. 1, 2, 3. Number 4 we're going to do together right now. Can you tell me which resistors are in series? Give me 1 second here. Looking at number 4, which resistors will have the same skiers, the same current, the same charges go through them? Suggestions. I'm sorry, I hear people whispering, but I'm not sure. Sorry? R6 and R8? Absolutely not. Some skiers go this way, some skiers go that way. Those are not in series. Sorry, but that definitely not series. R5 and R7? Absolutely not, because all the skiers that go through R5, some can go that way. Not all of them go through R7. Sanj? R2, R3, R4? No, because some skiers go this way, some skiers... You guys are way overcomplicating this. R3 and R4, all the same skiers have to go through those two hills? What else? There's one more. R7 and R8. All the same skiers go down those hills. Everything else, there's junctions. They can't be in series. Okay? Everything else, there's junctions. They can't be in series. What else? 6. We just did it. 6. 8. 9. Or is that a German? 9? Actually, 9, A and B. Okay. Look at number 11. Kayvon, we're going to do number 11 together. So I said so far 6. I said 8, yeah? I said no. 9, I'll come back to it later, but I got to get moving here. A and B. Okay. By the way, look up for a second. For what it's worth, on any one plug, if you're using a 15 amp breaker, you can run 18 100 watt light bulbs. You can run 7 250. Good gosh, Mr. Dueck, learn to read. Let's try this again. First of all, let's do this. In a standard household plug, part of the problem is that's a C right there. You can run 18 100 watt bulbs for what it's worth. You can run 7 televisions. You can run 180 little electric toothbrushes or about 2 toasters. Either or. In other words, 2 toasters, you try plugging in 3 toasters to the same plug off an extension cord, let's say, you'll almost certainly blow the breaker. Certainly if it's 800 watt toasters. Toasters would have a high wattage because they move a lot of heat around. Okay? But electric toothbrushes, hey, they use barely any power at all. You know what? You could run a whole bunch of those off of the same plug. We're going to do Kayvon. We're going to do number 11 together. Which resistors are in parallel? In which resistors do skiers shake hands, split up, and then meet up? Yes. There's one more. No. You know what, Doug? You could argue those guys as well, even though R4 also then splits up. It does come back together. I think R1 also, I think they both meet up right there. So yeah, R1 and R4 are in a very, not a simple parallel, in a complicated parallel. Yeah. (13 and 14). So the questions that I assigned for those who are unable to keep up: 1, 2, 3, 6, 8, 9, A, B, 13, 14. Believe it or not, guys, believe it or not, technically I should be able to give you the test tomorrow. In other words, If you understand at the end of today's lesson, everything that I do for the remainder of this unit is going to be, oh, here's a more difficult circuit, here's a more realistic circuit, here's a more difficult circuit, here's a more realistic circuit, but I'm not going to be teaching you anything new per se. How many more lessons are there? 5, 6, 7. And we're done.